ultrasonic sensor, and you probably have used this in the lab. Ultrasonic sensor is what is they call the time of flight sensor. Okay, what it does is basically sends the high frequency sound wave and measures the time to receive the sound wave, and that time is an indication of whether the obstacle of the distance of the obstacle or the object from the sensor. So the way this works is there's a transmitter, there's a receiver, and there's an object. And so the transmitter continuously sends high frequency sound waves to the object and waits for the echo back. And it cannot measure T1 and T2, but it can measure the sum in the following way. It produces a voltage which is proportional to the time. So the transmitter sends a signal, receiver received it, and it knows pretty much that it is received, and so it'll beep. But then you can measure the time because you know the delay between sending and receiving it. And so if you know that, then, and if you know the speed of sound, then you can compute the distance. It will be 2D because the sound wave has traveled to the object and back. So if you know the speed of sound and if you know the time, then you can find distance. But really, you don't really need to know this to know the speed of sound for such a sensor. All you need to do is you'll put an object at a known distance, D0, and you'll measure the voltage. Here, V is voltage. Okay. Once you have those two things, your new measurement, V1, this is for an unknown distance, D1, is given by this expression. This assumes that the voltage is proportional time and voltage is proportional to the distance. And so by equating the two, that is taking a linear proportions, you're able to figure out the distance given the voltage measurement. So this is measured. And this is your unknown. And this is your calibration constant. Okay, fairly simple. The same thing can be used for a infrared sensor. It just uses light waves in a different frequency. Okay, so this is a really simple sensor, and you can actually build it yourself. These are used in cars which respond to bumping into an obstacle. So the car bumps into an obstacle, and then it knows that it has bumped because it uses what is known as a bump sensor, and then they can turn and move. So the principle is kind of simple. It's basically there is a switch, and the switch is normally open, so no current is flowing. The moment an object is detected, it closes the switch. This leads to a voltage being non-zero, and if the voltage is non-zero, then you know that it has bumped, and then you can do something based on that sensor signal. Now, before here, there are two versions of potentiometers. There's a linear potentiometer and a rotary potentiometer. So linear potentiometer is used to measure linear distance. So the way this works is just ignore the part on the left. Just concentrate on this part. This is a simple circuit. There's a resistance, there is a current flowing, and there will be a current flowing depending on the voltage and the resistance of this wire. Now, this is a really long wire. What is done in a potentiometer, a linear potentiometer, is there is a wiper, and this wiper basically can be moved. As this wiper is usually placed on the object whose distance needs to be measured. So as the object moves, the wiper moves back and forth. And something we need to know, and I believe I talked about this a long time back, which is that the resistance of a conductor is given by this expression, rho times L divided by A. Rho is the conductivity, A is the cross-sectional area, and L is the length. So resistance is proportional to the length. That's the key thing we need here. For a length of wire L, the resistance is RL. Then for a distance of X, the resistance is going to be RX. So they are in simple linear relations. So you can find the resistance of this part, the part which is enclosed by the wiper, knowing the distance X, knowing the total length and the complete resistance of the wire. Now, it turns out that when you pass a voltage, the voltage is proportional to the resistance because the current is the same, the current is constant. So then we can relate the resistance here. Rx is replaced by Vx and RL is replaced by V. And we can derive an expression for X as a function of Vx, which is measured, V, which is the voltage source, L is the total length. So here, this expression, this is measured, and this is the unknown, which in this case is the distance measurement. The x is measured, so it's here. A rotary potentiometer works on the same principle. You need the corresponding capital L and V, and then you just measure the distance. So here the distance would be an angle. Probably if this is the 0 position, then this will be angle. And then that relation would be theta would be V theta, something like 360, or put pi there. So it's the total sweep. Let's say that the total sweep is 2 pi divided by V. So knowing V theta is measured, you can find the angle turn. And these are actually sometimes used to measure the angle turned by a shaft. Okay, a linear variable differential transformer is, or LVDT, as people call it, is another way of measuring the linear displacement. It works on the principle of electromagnetic induction. Okay, so this is schematic, shows how this works. There is a soft iron core. Okay, so this can be magnetized if you wind a wire across it. There is a primary coil, which is shown in red. There is a secondary coil, which is shown in blue. So a V in, a voltage is passed through the primary coil. What that does is magnetizes the soft iron cores, and that produces a current across the secondary coil, which then corresponds to a certain voltage out. Okay. Now, how is this used? Well, the voltage out is proportional to voltage in based on the number of coils in the secondary and primary. So this is an expression which tells you how to relate the V out and V in. If you have the same number of coils, then clearly V out is V in. And this makes the calculation very easy. This is the principle. The way this is used is as follows. Okay. There is a rod. Okay. And we want to basically attach this rod to the object whose distance we want to measure. So in other words, you want to measure the displacement of the rod here. So what is done here is there is a primary coil as shown in red. Okay. It's in the middle approximately. And then there's a secondary coil, which is wound in this fashion. This is a specific way of winding it, is that it passes through the ends. Okay. Now what happens is, normally when the object, or this yellow part, which is actually also the soft iron core, is at the middle, the voltage produced by the left of the secondary coil and the right half of the secondary coil are essentially equal and opposite. So the output voltage is 0. The moment you move this soft iron core to the right, more number of coils pass. There are more number of coils are on the right side and the left side, because this is going to leave the coils on the left side. And you'll see that the net voltage output on the right side related to the left, which means that you can relate the voltage to the displacement. Okay, and the same thing works for the other way. If you want to move this soft iron to the left, then you'll have more coils on one end rather than the other, which then introduces a voltage output, which can then be related to the displacement. So it's a simple sense that it produces a voltage proportional displacement. But the key thing here is the way you wrap it around. Okay, so radio frequency identification, or RFID sensors, are wireless proximity sensors. Okay, there are 3 elements to it: an RFID tag, an RFID transceiver, and an antenna. So the way this is done is, let's say there's an object to track that's attached to RFID tag that is connected to an antenna. On the other side, we have an RFID receiver. Now, what the RFID transceiver does is it shines some, it sends basically frequency data. It sort of energizes the antenna. Okay, so this is powering the tag. Okay, so this energy makes the antenna or the RFID tag send certain data to the RFID transceiver, and based on this data, it's able to identify the tag. that can go to a computer. Okay, so the advantage of this setup, which is really nice, is that this part is passive. You do not need to mount anything on the object to track. And this one is powered. Okay. So here the RFID tag sends data, and this data can contain some unique code which can identify which tag it is. So you could put one RFID tag on one object, another RFID tag on another object, and they have different codes, so you can identify each of them. Now, this kind of system is used in highway toll collection. So the easy pass which you put in your car is basically this part, RFID tag, which is an antenna. It's passive, it's not powered. You never have to connect it to a power source. But then when you go on a toll system, the toll system basically sends there's a transceiver which energizes the RFID tag and then collects data from there. So that's how the highway toll collection system in the US works.